Welcome everyone to a fresh set of exercises, this time covering chapters 9 and 10 of the book. And we will kick off this meeting with exercise 9.2. And exercise 9.2 brings to you the production of widgets. And widgets are actually only a thing that you come across in economics, so you may feel very special. And in our field, they denote very abstract units of production. It's not completely true. More recently, also in the field of computing, the term widgets is used, and there it is used to denote elements that make up the graphical user interface of applications. So think of buttons, scroll bars, checkboxes, labels, panels, or option buttons. So you're not alone in using the term widgets. Which brings us to question 9.2. So the production function that is given here is denoted Q is equal to a function of capital and labor as given. And we are asked in question 1 to fix the capital level at 10. So we're in the short run, we cannot change the level of capital. And we need to graph the total and average productivity of labor. So what we need to do is put labor on the x-axis and then the total productivity and the average productivity on the y-axis. And then at what level of labor input does this average productivity reach a maximum, and how many widgets are produced at that point? Now, this is just elementary math that we do in this exercise, so it's not that difficult. We have a production function as given. You need to know that indeed, if you have to map total productivity as a function of labor, then labor is on the x-axis and total productivity on the y-axis. So that is something that you already can draw. We fix capital at a level of 10. So we can just replace the k in the expression with 10, then you get the following expression. And of course, we have q on the y-axis, and we rewrite it a little bit because we have a quadratic term and then a linear term in labor and then a constant. And this is very similar to what you learned in Math 1, because it's an expression of the form y is ax squared plus bx plus c. And what you know is that for a being positive, the coefficient in front of the quadratic term, if it's positive, then you have a U-shaped curve, and if a is negative, then you have an inverted U-shape. And you also know that the top of such a curve is at minus b divided by 2a, and the intersection with the x-axis, so where y is equal to 0, the solution to that you find by using the ABC formula. So in our case, we know that a is minus 0.2, so it's negative. So we have an inverted U shape, b is equal to 10, and c is equal to minus 80. And now what we need to do is we have to find the top of this curve, which is at minus b divided by 2a, and the intersection with the x-axis, which we find by applying the ABC formula. Well, doing that, we arrive at the top being reached at a level of quantity of labor of 25. And the intersection with the x-axis, well, we put this to 0, then we solve for L using the ABC formula. We have two 0 points here, which correspond to L being equal to 10 or L being equal to 40. So at a level of 25, plugging it in our original expression, we know that if we use 10 units of capital plus 25 units of labor, then we reach a total productivity of 45 units. That answers the first question. And the points where it intersects with the x-axis are equal to 10 and 40. So for the average productivity of labor, so that's defined as well, the quantity that you produce divided by the number of units of labor that you use. So the average productivity of labor is the total productivity divided by the units of labor. So it's Q divided by L. Now, yeah, then you can divide this expression given here by L, and you arrive at 10 minus 80 over L minus 0.2 L. And of course, you can also represent the average productivity by this line over here. So, which is also Q divided by L. And the maximum is reached at, well, you take the derivative of the average productivity with respect to L, then you equate that to 0 and you find the maximum level. And doing so, you arrive at L being equal to 20. So if you are given 10 units of capital, then you need to append that with 20 units of labor in order to reach your highest average productivity. And in this curve, so here on the x-axis you have the 20, and this is the point where the average productivity becomes tangent to our production function. So it's the highest point that we can reach. And at that level, you use 20 units of labor, 10 units of capital. Your total production is equal to 40, which means that your average productivity of labor at that point is 2, because 40 units produced with 20 units of labor, 40 divided by 20 is 2. Now, we will make this in another graph on the next slide, where we also answer question B. And question B is again assuming that capital is equal to 10 units, graph the marginal productivity of labor curve. And at what level of labor input does this marginal productivity of labor become 0? Now, easy question. So our average productivity of labor curve can be drawn as follows. So actually for any quantity of labor that you produce, you divide the production at that level by the number of units of labor used. So actually we draw the curve corresponding to this function here. That's the one that's depicted over here, and you can indeed see that it reaches a maximum at 20 units of labor, and there the average productivity becomes equal to 2. But now for the marginal productivity of labor, well, it's the total productivity of labor divided, or the derivative of the total productivity of labor with derivative with respect to labor. So doing that, you arrive at 10 minus 0.4 L. And we are asked to come up with the number of units of labor for which is marginal productivity of labor is equal to 0. So we equate this expression to 0 and solve for L, and we arrive at the value of L of 25. Now, of course, this function can also easily be depicted in the graph at the right. So it's a linear function. If L is equal to 0, then it intersects with the y-axis at the level of 10. And if we plug in 25, then it becomes equal to 0. And yeah, that gives us the marginal productivity of labor curve. So, and by the way, where it says 0.4 here, it should be 0.4, of course. Then on a side note, you can see that the marginal productivity of labor curve crosses the average productivity of labor curve at its maximum, and that's not a coincidence. Actually, you can derive that. So the average productivity of labor curve by definition reaches its maximum when the derivative with respect to labor is equal to 0. Then you can, now we replace this average productivity by Q over L. You apply the quotient rule in doing that, then you rewrite a little bit, and this expression over here that you arrive at is similar to left-hand side. It's the derivative of the production function with respect to labor, so it's the marginal productivity of labor. On the right-hand side we have production divided by the number of units of labor that you use, which is the average productivity of labor. So indeed, at the maximum, which is the condition given here, of the average productivity of labor curve, the average productivity of labor curve needs to intersect with the marginal productivity of labor curve. And that as a side note. And then we arrive at question C. Similar thing that you need to do. So a bit of a boring exercise at this point. Suppose that the capital inputs were increased to 20. How would your answers to part A and B change? Now, this is a very good exercise for you to test whether you comprehended what we did before. So I asked you to do this yourself. And if you do it well, then you will find that the average productivity of labor is maximized now at 40 units of labor. Then the total production will be 160. The marginal productivity of labor reaches 0 if you will use 50 units of labor, because now the expression for the marginal productivity of labor will become 20 minus 0.4 L. Then finally, we need to do a short final question, which is question D. Does the widget production function exhibit constant, increasing or decreasing returns to scale? You can answer this question rather mechanically. So you have this production function, and what you need to do is you multiply both the units of capital and labor with the same vector, call this vector T, and you will see what happens to your output, to your production. So you replace the K and L each with T times K, T times L, and then you solve for this equation, and then the trick always is to arrive at a certain multiple of the original production function by wrapping all the terms with the T's together. So if we do that, then you get this expression over here, and you can see if you peer into this a little bit that this equation is exactly T squared times the original production function that's given here, because the KL is over here, the minus 0.8 K squared is over here, the minus 0.2 L squared is over here, and all three terms get multiplied with T squared. So if we take T to be larger than 1, then we know that if we, so for example, take 2, we double both the number of units of capital and labor that we use, what will happen to our production? Well, our production will become 2 squared, so 4 times the original production level, meaning that we have increasing returns to scale in this production function. And that completes exercise 9.2.